Straight off the bat there. I want to talk about the exponential functions you're probably most familiar with, because this details all of them. The most familiar exponential function would be something like this. Okay, y equals 2 to the power of x. And so we could generate a table. We could have an x value and a y value. Okay, if x is 1, then y is going to be 2 to the power of 1, which is 2. If x is 2, then y is going to be 2 to the power of 2, 4. Okay, we can keep going. 2 to 4, sorry, that's 8, that's 16. All right, and so then we can imagine the graph of a 2. All right, we've got when x is 1, y is 2. When x is 2, y is 4. When x is 3, y is 8. And so it's going like this, isn't it? Okay, it's spiking upwards. We've heard about exponential growth. That's what an exponential graph is. Now we can have exponential growth. We can also have exponential decay, which is when it goes like that. All right. So you can see we've got all those 4 shapes there. Okay, so we've got an example here, and we're going to analyze that using these rules. We have the function 3 times 2 to the x take 1 take 5. All right. So here's the base function, a times b to the power of x take c plus d. And it tells us what all of those values do. All right. So c and d are the same. We use that notation the same for all functions that we deal with. Okay. D is very easy, isn't it? We've got this function, and then we're going to plus d to it. Okay. Here we've got this function, and then we're going to take 5. So you can think, if I've got a graph here, and then I take 5 from every value, I'm moving the whole thing down 1 unit. So we're going to say d is minus 5, moves f of x 5 units down. Okay. C is our horizontal translation. Now, when we talk about C, we talk about it as x take C. All right, so you can see the negatives correspond, right? So that means the value of C is positive 1. Okay, C is 1, which means it moves 1 unit to the right. Okay, it always moves C units, and so if we have positive 1, it's moving to the right. If C is negative 1, okay, so if C was, let's even say negative 2, if we have x take negative 2, we're going to have x plus 2. So if we have a plus up here, it's moving left. If we have a minus, it's moving right. I think I detailed that clearly in here. Okay, moves 1 unit right. Okay, and we've just written there A and B, so that's the second dot point. A and B control how steeply the function increases or decreases. All right, them together are dictating their shape, and I'm not going to list all of the constraints, but it's all of these here. They're the 4 possible combinations. Okay, so let's write that. A and B, so we've got A is 3, B is 2. Together these dictate shape and steepness. Okay. State the domain and range. All right. So, firstly, let's talk about the domain. All right. So we can see our second to bottom dot point there. This is for all exponential functions. The domain is always any possible value. All right. For all exponential functions, domain xer. The value x belongs to the set of all real numbers. It can take on any possible value. So that's the domain. Okay, and then the range. Okay, remember range is possible values of y. All right? And it says it's either, we've got an error already. Y is greater than d, or y is less than d, is what it should read, not x. Y is greater than d, or y is less than d. The reason for that is, okay, the two possible default shapes an exponential function can take is this one, okay, where there's an asymptote there and it's always above the asymptote, or this one, where it's always below the asymptote. Okay, so is y greater than d or is y less than d? They're the two possibilities. In this circumstance, we have positive value of a and a positive value of b. That's our first circumstance. So it's opening upwards. Okay, it's going like this, which means y has to be greater than d. What is our value of d? We've identified it already. 5. Okay, so we've pulled that out just from the information that's given to us. Another way we can access it is from our calculator. So let's pull our calculators out. Oh no. I need to renew my license. So. I'm going to have to use Desmos.
Driving suspended.
Yeah. For the calculator.
Ah, that makes more sense. So you ride your bike to school.
That's right, yeah. Okay, so let's go into the graph and let's graph this function. Yes, it is, yeah. Thank you. Good pick up. So this function is 3 times 2 to the power of Okay, and so the domain and range, we can even understand that from the graph, can't we? Okay, we can see that it exists for all values larger than -5, that this is an asymptote here. You can see that pretty clearly. And then it exists for all values above that. And the domain, if you keep zooming out, you will keep seeing that it does exist for all values of x as well. And we can even see this information from here as well. So I said the default function is 2 to the power of x. Okay, so the default function is 2 to the power of x. What we can see is it's moved down 5 units. And we can even see it's moved across 1 unit as well. So where can we see that most clearly? Like the fact that the y-intercept's lower. Okay, what's the next part? Graph the function. Okay, so I'll give you guys an opportunity to scribble that down quickly. Just do a rough sketch of it, of the red one. Okay, so on a graph, I'll sketch it and then I'll go through all the information. Okay, so let me talk about the things we need for the graph. Okay, so firstly, the shape. Okay, that's probably the most important thing. But if you just drew this shape with nothing else, you might get 1 mark. Okay, so we need to get the shape right. We need to label our axes always. Get in the habit of that. And also be aware, like in Year 12, we're not only going to be having x as our variable, we'll also have t for time, okay? So if we're talking about time, then on our x-axis we should use the variable t. We need to have any asymptotes, okay, or other features of the graph. So here I've sketched the asymptote with a dotted line, and I've labelled its value. The asymptote occurs at -5. We should have a scale. Okay, so that doesn't mean we need to go 1 all the way through to 10 out in each direction. That takes a long time, okay? You can go up by 2s, but really you only need, because you're doing it on a grid, you only need to dictate a couple of spaces to show that it does go on in each direction with that same scale. The other thing is the scale should match, okay? So where your shape is, all right, we're going to see in a moment, or like for example here, the y-intercept is -3.5. Okay, it's close enough, okay, for me, my purposes up here on the whiteboard. But if you have this scale right, and then you put the y-intercept there, and set it's -3.5, that's not right. Okay, so you need to match all, it should all be coherent, it should be a coherent system. Okay, part D, determine the value of the function when x is 3. There's 2 ways we can do this. We can go, when x is 3, we can plug it in here. 3 times 2, 3 take 1. Okay, the value of x is 3. Alright, and then we're just going to evaluate that using some bed maths, aren't we? We need to perform that first. So we've got 3 times 2 to 2. Bed maths says we do exponents first, so we're going to have 3 times 4. We've got 12, multiplication, and that leaves us with 7. Okay, that's one procedure we can do. The other way is to use our calculator. Alright, so in our calculator, we can G-solve. We want to know a y-calc. When x is 3, what's the value of y? It's 7. Alright. Another procedure you can use is just on your graph. If you press trace, F1, and then you just press the number 3, it'll take you to that location. It'll tell you the value of y when x is 3. You can press 5, it'll take you to that location as well. So we've got when x is 3, y is 7. That's part D. Part E, find the x-intercept using technology. Okay, so we're going to just G-solve the root. And I'll put it up here, it's like 1.737. Okay, now to 3 significant figures, that would be 1.74. Okay, and lastly, find the value of x when y is 2.3. So this time we're doing G-solve and we're doing an x calc. We want to know x when y is 2.3. And we'll get x 2.283. Excellent. All right, so I'll stop there. We can finish taking this down, and then we can open up to exercise 1A, and should be. Yeah, let's get into it. There's one thing I haven't printed for you guys.